Hello, everyone.
Good morning.
Morning, Micah.
Yeah, good morning.
Good morning.
I think we can get started on this. Mm, Can everyone see my screen?
Yeah,
Awesome. Okay. Okay. We have gotten feedback from OCP on the presentation. I'd like to go over that, and also I want to continue from our side. We were working on a presentation, and also I think today we have info, so I want to finish the last three slides that we were discussing last time. Really, talk to the last three slides. Any people control you?
Hello?
No.
The sound is not clear.
So,
can you hear me?
Yes, now it's good.
Yeah, I want to talk about the two-phase. Like last time we were discussing about the form factor, and after that, I want to continue on the coolant, like these two slides, like what kind of data we're presenting here, and how is that important to compare between single phase and two phase uh, heat exchangers. Like if we can like talk why as you are here and Leela is also here, can we talk about that for some time? Leela, like can you
Hi everyone.
anyone can you talk about the importance of this slide if you don't mind?
Yeah, I think we were trying to show an example.
Yeah, sorry
It's
to put you sorry to put you on spot.
no,
But
it's okay. This is giving you a connection between the inlet air temperature to the case temperature of the chip. This is actually the limitation of the condenser at this size, meaning that if you have a rack that is a 34 kilowatt, for example, that's the orange line, and you need case temperature that will be around 50. Then in that case, maximum air inlet could be 40 degrees. But if you would need it case temperature to be 40, for example, this is the temperature for the H100A, H100 GPUs, then you will need to limit the air temperature input to around 25. This is the connection between, that's what, I'm not sure it's part of this presentation, but this is what this graph is providing in a two-phase. And by the way, I did the calculation this week, and the form factor for the single phase and two phase is pretty similar.
okay.
There's not big difference. I was expecting it would be a bigger difference, but there isn't a big difference between the first single phase and two phase, because eventually it's all about the amount of air that you're flowing through the size of a rack.
Yeah. So what you meant by that is this this size on the like uh actually these okay, this dimensions, right? The height, width, and depth.
Yeah.
Okay. So they are similar to an IT rack. So as the single phase heat exchanger, right?
Yes, the only thing that I was puzzled is last discussion we had, we discussed that the width is 80 centimeter, 800 millimeters, but the ORV3 is 600 millimeters only. So I'm not sure here if we are correct with all the other dimensions.
No, actually, I didn't say any numbers. I only said either similar to ORV3 or a custom width. Like in all these dimensions, I never wanted to give a number out because the rack definition defines that. The IT rack definition defines that. So I in this context, what I wanted to put forth is the cooling rack or the AALC rack should be almost similar in dimension as ORV3, so that it can be also populated in place of ORV3 rack or any IT rack without having to create additional accommodations for that particular rack. Does that make sense?
Yes, but if you go back to the beginning, the slide with the two racks and single rack. No.
This one?
Yeah.
Okay.
So we should consider the sidecar here as being the same size, meaning if we're talking ORV, so this would be a 60 centimeter by 220. This would be the size of the sidecar.
This one, right?
Yeah.
Yes, this one is going to be the same as the IT rack um, in terms of width and depth, so as the height. I did not mention that here because like I want to just put it as a backup slide. So basically this dimensions here, like if you see even in this picture, they look identical because they should be identical.
Yeah, that one I get. It's just when we're getting down to calculations of airflow and CFM, then we should take we should give the calculation for our V3, I think, and we can also always say that it could be for different sizes.
Oh, yeah, that's true. You can say that it's for different sizes. Um, uh, the width calculation or the airflow calculation were done based on the capacity restrictions, and also what is the restrictions on the data center side and the airflow velocity restrictions on the heat exchanger side, right?
Yes.
Okay, so that's why we talked about airflow constrainment. Where was that? We were talking, yeah, we were working on that in one of these in this document actually, um, in the guidelines, product specification guidelines. So the manufacturer should provide certain airflow limitations, such as a CFM, the maximum airflow that the hardware can take. And the data center folks can decide how much they can provide, whether they can use all of it or they can limit to certain factor. But from the manufacturer perspective, they should provide one of these to make sure that they give a certain limitation on the airflow. So as the noise levels, it's noise levels pertaining to that particular airflow. I think this is what what you were talking about, right? In terms of airflow.
Yes.
Gotcha. Yes, so coming back to these two slides, yes, this slide tell us what could be the some of the equipment or manifold differences, um, or leak detection, so on and so forth. So do you think these are the major ones, or do you think these are the only differences that we have between single phase and two phase?
On the sidecar, probably yes, we can discuss also the pump side if you want to discuss, but pump power is in this kind of sidecar is actually redundant. I mean, compared to the fan power, it's not a big issue, I think.
Yeah. So, but you're gonna use similar type of pumps or same pumps for driving this, right?
Well, the pumps on two-phase are much smaller because the actual flow is about 10 to 15% of the flow of the single phase for the same power.
Mm-hmm.
So the pumps are smaller. And now I'm asking this question. Now you're talking about a sidecar. Where are the pumps here? Where are the CDU located? On the bottom of the
Usually,
same rack?
the pumps are located at the bottom for a sidecar, uh, somewhere over here. Like you see the RPU.
Yeah.
Usually most of them carry a pump and reservoir here to reduce the total center of gravity to lower it actually.
So do we discuss this in this paper, the size of the RPU or?
We can
Because that's
we can
also
talk
limiting
about
the
the
size.
reservoir capacity. Reservoir capacity is one of the terms that we can, I think that the manufacturer should provide. Based on that, reservoir capacity and total fill capacity is another term that can be used.
Okay.
Because like in every so especially in a single phase, you cannot have any air bubbles, which means you have to fill all the heat exchanger and the cooling loop with the fluid. So there is a certain volume associated with that. Total fill volume or capacity.
Yeah.
Now, is there a
And
connection between? Yeah, go ahead.
in this case, what about the safety? What happened if the pressure is increased or something like that? We must also take into consideration that safety valves or expansion valves or expansion tank should be in the system.
Safety valves, yeah, those are definitely also needed, like pressure safety valves. Like you need yes, the fluid will expand and contract based on the temperature. Um, and so as you want to have certain pressure inside the system itself, right? So for that, yes, you need some kind of a pressure controlling system that will allow the system to expand and contract as necessary. So yes, you need some kind of a pressure tank or something. I think that comes like does that also be in the specifications? Product spec? That's the question.
Yeah, it should be in the safety part on the specification, because if you design something like that and you didn't take into consideration that, it will be a big issue.
Yeah, I understand what you're saying, which means that is considered as a basic necessity in terms of safety. But this guidelines in terms of product specifications are for everyone to understand or compare and contrast between whatever their needs are versus whatever they're getting or they're buying. In order for them to understand that these specifications will be used, yes, additional safety specifications has to be written for sure. We can add that. I didn't think of that through, but would that be a critical component or non-critical component? Like, and will there be any failure rate associated to it?
You mean with the safety valve?
Yeah.
Also, the system can run without a safety valve.
System can run, even the safety valve fails?
Yeah, because the safety valve is only coming if the system, one part of the system, for example, in that case, in two-phase, the fans are not running anymore, but the pump is still running. Then we'll increase the pressure, and with the pressure, maybe the system could be damaged. In that case, we need a safety valve, but only in a failure mode. And there is another ways to solve the problem, disactivating, for example, the pump or something like that. Or so the safety valve is only a safety. Yeah, the system will still running in that case.
Mm-hmm. Okay, so this would be a non-critical component, and
It's a safety component.
No,
it-
in
This
my
is
shall I speak? In my opinion, it's critical component in data center application, because if the safety valve will open or any leakage happened in the product, then the liquid will flood it and make the component of the data center not working. And sometimes it's so it's high critical and safety issue for data center application,
okay,
which
gotcha.
means that if you build a safety valve, you must know where, in the case of high pressure, where is the extra liquid will go, or
Gotcha.
yeah.
Yeah, but I think that when we spoke about the critical components, is critical components to supply the liquid. And there is another critical components like for safety. I think there are two. I don't know. Maybe we can put everything in the same place, but are two different ways. For sure, if the valve open, then this is a critical component because the water will flow outside the system, and yeah, in that case will not work anymore.
Okay. 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 Having said that, like I think that's we can put that in a non-critical component, but still has to be uh, like replaced or worked on. Um, okay. Sorry, I think I derailed from the two-phase topic, so I'm gonna go back to that. Sahar. So we were talking about, so we'll still be using the pumps. They're still comparable to the single phase and two phase have still comparable pumps. Uh,
I
which
think that
means,
we should easily put here the flow rate. That is in the single phase, it's like 1.5 liter per minute for every kilowatt.
mm-hmm.
And for two phase, it's 0.3 liter per every kilowatt. That would give a number for any quantity
Well,
on the
okay, like,
comparison side.
do you mind sharing like how did you get that 0.3 kilowatt? Is that a calculation?
That based on actually in two phase, this is the amount that has been evaporated for 1 kilowatt of power. It's a very constant number, it's linear.
So is that also dependent on vapor quality or no?
No, the pump
No,
don't control the vapor quality. Vapor quality is in the
controlled by the
evaporators.
power. I know the cold plate. So is that the assumption that the vapor quality it is
Is
100%
100%.
vapor?
Yes.
Okay, gotcha. So if it is less than 100% vapor, then
The
it's going to
amount of
be
liquid
different.
needs, yeah, the amount of liquid needs to be higher, yeah.
Okay.
I have a small question. What about what type of dielectric liquid you are speaking about? There are a specific, because I worked a lot with dielectric liquid in immersion cooling application, and in my opinion, the kinematic viscosity of it's very high, and the power consumption is
No, but
higher than.
you're talking about single phase immersion, not two phase immersion.
Okay,
in-
because you are writing now two-phase immersion.
It-
Two,
it's not
two-phase
immersion
total.
cooling.
yeah, it's
everything is
yeah,
total.
I know, but I mean about the liquid, because a few minutes ago you said the pumping power can be neglected, but in the case of dielectric cooling, is not neglected, in my opinion.
No, the electric liquid here that boils at low temperature, like the 1233 ZD or the SF33, those are viscosity is very low, meaning it's not
Kinematic
not
viscosity is
highly
less than water, yeah. Okay.
no, it's very easy to pump it. The only thing is low amount of liquid per minute compared to if you divide by kilowatt.
Okay. Yeah,
That's a
because there are
difference. But
many
still,
types of dielectric that I asked you. Yeah. Okay.
but still the fan power in this kind of solution is very high, much higher than the pump power. But the majority of the power in these kind of solution would be for the fans, and the fan power is actually connected to the mesh of the condenser, the radiator.
Mm-hmm.
So this is a different discussion, not connected to. But I'm saying, in general, Sidecar has much more power for fans than for pumps. That's my
Yeah.
opinion. If I'm wrong here, then
No, it's right. Also, I think here is for the customer point of view.
right.
The differences between single phase and two phase is that the pump consumption is less by two phase because you have
I think
to push less flow rate there, like
yeah,
than water.
I think the main difference for this document would be the size of the pumps, because the RDU takes part of the area of the condenser or the radiator, sorry.
I don't know. Also, from the other side, you need a bigger accumulator for the liquid to separate the liquid and the gas. So
Yeah.
I think we'll compensate it. I think for the customer point of view is the fan power will be the same, but the pump power will be a little bit lower.
Yeah, but
If
the
you
question
compare.
I'm asking is, does it have a difference because of the size of the pump is different? The pumping and the buffer are all smaller. So I think the RDU will be smaller. I'm not sure at the moment. And if it's smaller, then you have more size of, maybe it's neglectable.
So
Maybe we
I
can
think
debate.
in 3U it's possible to put the pumps inside the RPO in
Yeah,
3U
okay.
for
If
these
3U
60
is enough
kilowatts. Yeah.
for water, okay. For single phase.
Yes. But for the point of view of the customers, if I will be customers, for me it's interesting. The consumption is higher or lower. We can say, okay, for the pumping, you save a little bit energy because you have not to pump too much liquid flow rate. The liquid pipe will be smaller, but the gas pipe may be bigger. And this is the difference between two phase and one phase.
Yes.
Okay.
In terms of that 1.5, sorry. So OCP right now, the range in the cooling guidelines is 1.25 to 2. And that's on a 10 degrees Celsius temperature rise. Right? That's a single phase PG25. We don't have that kind of data, or sorry, we haven't stated what the assumption is for the two phase in terms of the liquid. So I think that's important. Right, we have it for the single, but not for the two phase. So we need to probably include that information somewhere.
Yeah, we haven't stated any properties of the dielectric fluid here, except for having a low boiling point and having some A1 safety certifications, or like in classification to A1 envelope. Is there anything that we can add here? Because like PG25 on water with additives, like it's almost publicly known, those properties. So is there anything that we can add here that can help narrow down?
We can put maybe examples if wanted, if that would help for specific liquids that could be used.
Sure, I think that might clarify a few things.
And
Okay,
remember,
then
this
we'll
is going into a white paper eventually, so it's even if you don't put it in the presentation, it's going to have to be in the white paper.
Yeah, it has to be. Yeah. We I think in the white paper it's going to be more detailed, but here it's just going to be for an FYI sake.
And
Okay.
also when you're presenting, Rajesh, because I have a feeling whenever there's a figure on the screen, especially just one like this, usually people ask a question about it.
I want to have certain, at least some examples that are widely used, because there is no more Novak fluids coming, right? So what are the fluids that exist in the market that can be used into this is something that even I am curious about.
You want it now, or you wanted to add it to the Y? I can give it to you now. It's R-1233 ZD. ZD, small z and small d.
Okay.
And there's also it's called SF33, or let's go R1236, I think. You'll have to remember the number of SF33, or call it SF33, the second one.
Okay.
It's called it's at the name of it, the commercial name.
And these are commercially available fluids in the market.
Yes.
Gotcha.
From companies like Honeywell, Chemross, and others.
Okay, gotcha. Yeah, this is just to be in handy if someone asks, not saying this should be used, but just to say, yes, there are some fluids that already exist, and these are some of them that are being tested or used in the industry.
I'll
Yeah.
I'll add to the white paper the exact names, the non-commercial names, but the real, names that are non-part of a commercial name.
So
Okay.
if you can put that in, like, I'm gonna copy this into the chat. If you can put this, there we go. If you can put this in this part, in this section somewhere, in the especially in the two-phase section, either here or in the design. Yes, I think here somewhere. In the material section, that would be great. Some standards, like if you can link some white papers pertaining to that would be great.
Sure. Simple.
And 1.5 LPM is not like a fixed standard. This is like a generally used.
This is a figure that was published by Intel, and it is a generally used figure.
Yeah, but it's function of the temperature difference for fluid flow rate.
Yeah.
1.5, it's related to 10-degree difference between the cold and hot liquid. But I draw some function for that, and I found it's 15 divided by delta T, which means that in this case, delta T is 10, 1.5. If it's 5, it will be different than this.
Yes.
And I can share that in the this graph what I did. You can open it, and in most cases I found it's between 1.5 to 2 liter per minute per kilowatt.
Gotcha. Okay.
That's the range from OCP as well, 1.5, 1.25 to 2 for the centigrade cell.
Yes. That's correct. I attach the drawing, and you can also look to it if you like.
Yes, please.
In chat, yeah.
Okay, yeah, this is good. So I need to figure out how I can tie this. This is very useful data for sure, but I want to figure out like how we can tie this to the single phase versus two phase on this. That is something.
Do we have something similar from a single phase? Maybe we can simplify it in two different graphs. This has three, but we can take only one of them if we want.
I understand, but this is
But this is difficult because this is only a commercial performance of one defined reorder.
yeah, this is
Because if you want to compare the two phase and one phase, you have to take the same heat exchanger, modify for sure some connections, the same system fans and so on. And this is the comparison is difficult because you are comparing two rear door heat exchangers, the performance of two rear door heat exchangers from the commercial point of view, and not the technology with this graph. This, if you want to compare the technology, you have to compare the heat transfer of the refrigerant versus the water. But for the people will not be very interesting because it's only one number.
Yeah, that at least like we cannot have a single phase comparison for saturated temperature versus air inlet temperature. That is not a fair comparison.
Yes, this is the same. The saturation temperature is like the temperature of the water.
Well,
the cold water temperature is very similar to the saturation temperature.
Correct.
If you want to compare. And then you have the power and the air inlet temperature. At least you are comparing the approach 43 to 33. You have a 10 Kelvin approach. For this 10 Kelvin approach, you have 22.8 kilowatts with this heat exchanger at maximum velocity fan speed, something like that.
Interesting. So we can take something like there is coolant flow rate. Yeah, we have airflow rate here, and then we can take hot air or like the cold water temperature or the written water temperature on the heat exchanger and compare that with this. Is that a fair comparison then?
Well, at least it's a comparison. I'm not sure if it's fair, but it's a comparison.
That's why, like, I think a better comparison would be what is the heat transfer happening? How much of heat is being rejected at different temperatures, different inlet temperatures, which you have here. But instead of a saturated temperature, is there any other parameter that we can use, like a inlet temperature or of liquid or
in two-phase, the liquid temperature doesn't have any effect. It is related, but it doesn't have an effect on the cooling.
Yeah, it's all about latent heat, right?
Yeah.
Yeah. Okay. Yeah, so that's why I kind of I don't know how to relate this with the single phase comparison. If anyone have any ideas, like I'm happy to take that. Otherwise,
I
I
would
don't know how to
easily,
use this slide.
yeah, I would say that if we don't have any comparison, let's lose this slide altogether.
Yeah, I'll just keep it as backup for now. But yeah, I think this is the only slide we have for the comparison. In that case.
Well, the other parts, the mechanical parts, are actually the same. It doesn't
Yeah.
matter if it's a single or two-phase.
Yeah.
Tubing is very much the same. So
Yeah, there are some parts where like you try to remove the water bubbles from the flow in a single phase. In the two phase, you don't do that.
right.
Um, through the filtration process, you remove any air bubbles inside the water loop or the PG25 loop in a single phase versus in a two phase, you maintain the pressure with the help of like saturation temperature or flow rate, something like that. Okay, now this is a little bit more clear for me. Yeah, thank you. Okay, is there anyone from Vivian that can help me with some of these slides? Are no one in this call? Okay.
What do you mean with that? Sorry.
Vivian helped me with this data, and I'm thinking they can go through the data once if possible.
Hello, Josh, and I'm Willie from Within Team, and maybe I can just go through these 2 pages of our sharing. But sorry, I have to say I'm not a presenter of this topic in this project.
I understand.
Yes, I can just help to briefly explain how we want to share in this project.
Yes, please.
Okay, so the first is the first is our test condition, which we use the phase coolant supply temp and sorry and thermal expenditure of the coolant. So once the operating coolant flow rate will increase along the cooling load. And the second is what we found in our test resource, and we can sorry, I think there's some typo on the flow rate, and exactly we can see the graph on the left. The linear line should be the orange one, and which is represent the coolant flow rate. So I think the airflow rate in the second point will need to revise to the coolant flow rate. Yes, I think there's some typo on this document.
Oh, okay. So between this and this, I didn't understand what's the typo here.
Yes, in the point we say the flow rate increase almost linearly with the increased heat load, but exactly the linear one is the coolant flow rate, not the airflow rate.
Okay, increasing the heat
Yes,
load.
yes.
Okay.
Yes, so the airflow rate should be revised to the coolant flow rate. Yes.
Yeah, can you double check on that and get back to me, please?
Okay, maybe I can check the information internally.
Yeah.
Well, I don't understand why it's not linear, these two curves, because if you increase the power and you are able to increase the flow rate as well, which is not right, but if you have to increase the flow rate with the power of the flow rate of the water, then the airflow rate should increase also in parallel, not like an exponential.
Yeah, and another thing is this rear door heat exchanger data only? Can you confirm whether this is a rear-door heat exchanger data or a CDU heat exchanger data, which is not said here?
I don't know. I don't know. But the heat of the chip will be removed through the water with and the mass flow multiplied by the constant by the delta
Yeah.
T is the equation. So
Yeah,
if
Q
you
is equal to
increase
1
it,
CP delta
if
T.
you increase linearly the power, you will increase linearly maintaining the delta T, the flow rate.
The
And
this
the
will
for
be okay.
for the air, I suppose the same.
No, airflow might be different, right? Airflow rate. Oh yeah, it's almost the same. That's true. Your mass flow rate is volume into flow, volume into density. Yes, ideally they should be the same.
Yeah, the difficult here is in the system, in the real system, you don't modify the flow rate with the power. Flow rate usually is constant. You change the temperature to accommodate the power.
Yeah.
Therefore, it's difficult here to make that.
Yeah. Billy, could you help me clarify on this? On these
Maybe.
2 points. No,
Yeah.
not the first point, actually, the second point,
Yes.
and this. They are not consistent. One. The other one is this doesn't compare the data between rear-door heat exchanger and the sidecar heat exchanger. I would appreciate it if we can change this graph.
Okay, maybe I can check with our presenter. And
Yes.
Roger, just can you also send a formal email to us, and we can record the point which we want to clarify.
Okay, sure, I will.
Thank you.
You have everyone's email, right, Rajesh? Like
I
who's on the call
do.
now?
I
Okay.
do. Yeah. Thank you. Okay, let's continue in the next slide.
And this slide will be which our purpose is to find the most the most operated the most efficiency operating condition which we should set the pump duty and the fan duty of the AALC system. And in this graph, we can see that the fan power out in the AALC system accounts for a large proportion. So even we turn or even we reduce the fan duty and increase the pump duty alone, and even sorry. Even increase the pump duty to the maximum power, sorry, I think we should. Okay, so to minimize the power consumption, we only what we only can do is to maximize the pump power and lowers the fan power. So
What is the
yes.
purpose of this? Like, what is the purpose of changing the flow rate of the fan and the pump to maximum to minimum?
It's because we want to find the most efficient. We want to find the most efficient operating points, which we want to see if the fan power will be the contribute most of the power, or the pump power will be the higher.
Okay, so this is compared for both CDU and radio heat exchanger, and you're saying for radio heat exchanger, the total power consumption goes down, and for the CDU, total power consumption will go up.
Yeah.
Is that right?
Yeah, that's correct.
Okay. Do you know the reason why this happens?
You mean the tendency of the total power consumption?
Yeah,
or
why the power consumption increase for the CDU and reduce for radio heat exchanger? Yeah, yeah, because like these questions, I think it's good to note down why that's happening as one of the bullet points for CDU versus radio heat exchanger. That would help explain better.
I'm not quite sure how to help you with that.
Do you understand me, Willie?
Oh, okay. So you mean the purpose why we reduce?
No, not the purpose. What I'm saying is why is there a
Why is
decrease
the
in
tendency?
power for heat exchanger, and why is there increase in power for CDU? What's the reason behind it? It would be good to have at least one or two sentences on that.
Oh.
You could probably put it into the email that you're sending out, Rajesh. So that
I'm
because
gonna.
I think there are a number of ways you could probably answer that, either in physically with the flow rate and the door heat exchanger in terms of which is probably better, the actual formula that's being used and looking at what's varying as the coolant flow rate increases. So yeah, I'm sure there are a number of ways where they can answer. So
yeah. And the last one, I think this is little straightforward, and the power consumption come from directly, the majority of the power consumption from the heat from the CDU is from the fan. So I think this kind of makes sense. Power is directly correlated to the airflow, because majority is coming from that, and from pumps it's minor power, and the approach temperature is directly proportional to the airflow that you use to get that. Like flow rate will also help a little bit, but airflow is the major factor that's going to impact the approach temperature. So in this it is a little bit more clear for me, but for the top two slides, it's not that clear, and it would be nice to have one sentence for this on the reason, and for this it would be like adjusting this curve, and having a better one comparison between CDU and heat exchanger would help in this. Yeah, I'm gonna type all of this in the feedback and send that as an email for an action item if possible. I have to submit the revised slides by 26th, which is the next week, next Thursday. I would appreciate it if you can get back to me with an answer or an updated slides. That would help me in submission. Thank you. Yeah, thank you, Willie.
Yes, thank you. That will make sense.
Yeah. Yeah, we are. If anyone have any other suggestions or questions,
yeah, just one. So and when you were the slide that was comparing single and two phase. So I know we said we'll keep it as backup because of the we had a saturation temperature. We were using that as the basis. But we did quote the 1.5 liter versus the 0.3. And I'm wondering if there was a way to compare single and two phase using the flow rate versus total cooling power consumption.
Flow rate versus total cooling. I think that's difficult because the flow rate on this is dependent on the on the quality, vapor quality. But I think I'll let Sahar or Leela answer this question.
You're correct. Maybe it's worthwhile putting a comment that is at 100% vapor quality or something like that. This is a comment next to it.
Okay.
Also, small question, why no need for water leak detector? The two phase.
There is no water in the system.
Yeah, but what happened if some leakage happened?
It evaporates.
Yeah,
So
which means that you need leak detector.
yeah, but
Yeah,
leak detector
leak
doesn't
detector.
affect the only way to detect leak in the electric liquid that is evaporating is by monitoring the buffer side, the liquid in the buffer. Because the vapor immediately evaporates. There is no
But
drops or anything
even
like
we
that.
build CDUs, which is also have leak detector. The safety is number one in data application, and I think no one will accept system without no leak detector system. But that's my mind, and you can.
Yeah, I understand. Like leak detection is important in both aspects because, I mean, this two-phase liquids are even a little bit more expensive, and they need to be a little bit more expensive than the PG25 or water. The administrator would want to know whether if there is a leak and it's draining, they need to know, which means they need some kind of a sensor to identify the leak and like have report it. But that depends upon that the leak detection mechanism depends upon, I think, different manufacturer. I cannot dictate what kind of leak mechanism they have to use. All I can say is yes, they need to have some kind of a leak detection mechanism to make sure that for both safety and also not to lose any fluid to the environment. That definitely makes sense. Yeah.
Yeah, but maybe instead of no need for water leak detectors, you can write leak is detected by the level of the liquid in the buffer.
Okay, gotcha.
Mm-hmm.
But that takes some time, I guess, right? Like in terms of, I mean,
but instead of stating no need for it, I think it would be better.
okay.
Mm-hmm.
You already have pressure sensors in place to identify some of the like inlet and outlet pressures to make sure the saturation temperatures are in line with what you require, right? Or is there any pressure sensor that
Yes.
can, yeah.
Yes, there is pressure and temperature sensors.
Gotcha. Okay, we'll add that to the safety requirements in terms of leak detection and pressure maintenance, so on and so forth. We'll continue the topic. Thank you. I think we are 1 minute past 10, so I don't want to take much of everyone's time. Thank you for today's meeting. It's a great discussion. I will use this feedback to submit my next week's presentation. and I'll work with Vivin offline to get their updates. Thank you, everyone.
Thank you.
See you.
Thanks. Bye-bye.
Bye-bye. Yeah.